Okay, I believe it's recording. I'll just give a quick walk through the two network files that I've explored and um, tried to understand the network architecture from them. So the first file is two-dimensional convnet.py. This is a file which uses TensorFlow, as we know. So this is the first function, define weight variable, as we know that each layer in the neural network have certain set of weights associated with it. So this layer is actually using an input parameter. This function is using an input parameter shape, and the main function here is that it is using tf.get variable, which is a way of creating a new variable in TensorFlow. And it also comes with a built-in initializer, that how do you want to populate the values of the variable that you want to create with this shape, and this is the name of the variable. The default name for all the weights is going to be w. Same is the case with the bias variable. In addition to weight variable, we also know that each layer have an associated bias with it, so they are trying to do the same thing with tf.get variable. Then they are using the conv2d function to use the tf.nn.convolution function to actually make a convolutional layer. And if the draw rate is greater than 1, then they're making a simple convolution layer, and if it's greater than 1, if it's not the case, then they're using a conv2d function in which the strides are kept fixed and the padding is kept to same. The same padding means that when a network is a layer of the convolutional network is using padding equal to same, that means the size of the input and output image through a convolution layer would be same, because we know that the convolutional layer reduces the resolution of the output. So padding equal to same actually saves us from that, and it pads the input in such a way that the output size is equal to the input size. This function right here is the star of this file. So this is make convolution separable 2D layer. Separable convolution, you guys should go through the article that I shared. It's a type of convolutional layer which actually breaks a convolutional layer into two steps. The first is a channel wise operation, and the second one is a 1x1 convolutional operation. So these are the parameters, and filter size here, the main thing is the rest of the parameters are quite self-explanatory. Channel multiplier is something that is associated with the separable convolutional layers. It's usually 1, so in this case it's also 1. That is so basically in a separable convolution layer, we kind of divide the convolutional operation into two steps. So first is a channel wise application of kernel onto each channel of the input image, and the second step is to apply a 1x1 or 2x2 or whatever size you specify here throughout the output channels that you got from the first step, the feature maps that you got from the first step. I hope it will make sense once you will read the article, the one that I've shared here. Sorry, this one. So with that, then we have so filter size 2 is, you can think of it as width and height, and then we have a depth. So we don't have any depth here, that is channel number in case of out channel, or channel number in case of convolution. And filter size, you can think of it as width, and filter size 2 is height. So that is set to none, because by default in every function, if that is set to none, then we keep it we actually copy the filter size value, the width value, to the height. So with tf.variable scope, this is a way of defining a scope in which we want this next piece of code that is going to be indented or coming under this area to be considered or to work. So then all these indented lines of code will be related to this scope, which is being named with this layer. So we have in this layer we have two possible scopes. First is the depth wise, and the second is point wise. So the depth wise is the first operation of a separable convolution layer, which is we apply a kernel separately to each layer of the, or each channel of the input, and that is what they are doing here. They are defining a weight variable using the weight variable function, giving the filter size to input channel and channel multiplier with the standard deviation. So this is weight depth wise. And then they are defining pointwise, which I said is a 1x1 convolution. So they are specifying the height and width as 1. And input channels is multiplied by channel multiplier, because the number of channels is going to be equal to the channel multiplier. If it's 2, then it's going to be 16 into 2, 32, for example, if we want the output channels to be that. And that is the value for the output channels. I don't know if I'm making any sense in this one, but I'm actually this is the value for the input channels, and once it passes through this layer, the value of the input channels is changed to input channels multiplied by channel multiplier. So the input channel for the next layer is the product of the two, and then we have the output channels, which is the number of desired channels that we wanted to have. And then that's it. We use the built-in separable conv 2D layer function with all these already set parameters, which you should note that it is outside the individual scope of these two weight defining functions, or weight defining scopes, and it's within this layer scope. So we use the depth wise and point wise weights, which is what we actually pass to the separable conv 2D layer to actually get our horizontal convolutional layer output. Then we have batch norm. So if batch norm boolean is set to be true, so we use the batch norm layer function, which is up there, and that function uses an input layer, the name of layer, if you want to set the training to true, and the data format, which is batch number, height, width, and channels, and HWC. If you have not set it to true, then instead of using a batch normalization layer, we actually get a bias variable, and then we add this bias variable with the help of a bias add function to the weights of this hconv layer, and we return it. So this is the main function here, the make separable conv separable 2D layer. Then we have the batch norm layer function. Simply it's using this built-in batch normalization function with using some built-in parameters to call this function. And then there is this make conv layer. So this is creating a convolution layer, as you guys can see, and this is also using the same approach of setting the width to height if one of them is none, and it's doing the same thing. But over here you can see that we don't have any depth wise or point wise scope, just the layer scope, because there is no such scenario in a typical convolution layer. So we are defining the weights using this weight variable function, and then using the conv2d function of the conv2d layer, we are passing in the input node, the weights, the rate, the data format, and we are getting the horizontal convolution layer. And the same operation is again here, and if there is a non-linearity specified, then that was exponential linear unit, we pass it through it, and we return hconv. So these are the functions that are actually defined in this file, and not much. Then is this 2D Resnet, two-dimensional Resnet file. So in this file, they are importing the two-dimensional Convnet file, the one that we just saw. So they're going to use the functions described there over here. The first one is make separable Resnet layer. So the separable Resnet layer, you need to see that it's a layer. It's not a network or not a bunch of layers, but just a single layer. So let's see how it's gonna be done. So it's a separable Resnet block. So you can see the sequence that is being specified here. You'd be able to see this sequence in this once I'll walk you through it. So what are we doing? That we are starting the scope with the name of the layer, and we are saying that input times almost 1 equals to input node, and horizontal conv is equal to input times almost 1. So what is the point of doing this kind of pointless assignment here? It's for making this skip connection. We are trying to save the input information at the start in a redundant variable, so that we could use it again at the end towards the submission, for the submission. Yes. Okay. So we are starting off with the batch normalization layer, which we have already seen is the first one. So if batch norm is set to true, so the two-dimensional convnet dot batch norm layer. So we are calling this function from the two-dimensional convnet layer, and we are setting it to hconv. Then we are passing this hconv through the exponential linear unit nonlinearity, which is right here. Then we scale it down. In convolutional neural networks, to scale down the output from the previous layer, there is something called 1x1 convolution, and that could be done by setting in that in the 1x1 convolution, the kernel size is 1x1, and the number of channels is set to the size which you want for the output channels. So this is something you guys can think of, an operation that is supported in CNNs to scale up or scale down the number of channels of the previous layer. So in this case, as we know that they are scaling down the number of channels, they are dividing it by 2. 128's half is 64. So we want to scale down the number of channels to 64 without making any changes. So this is just a simple make conv layer, but here the filter size, that is height and width, as you can see, is set to 1, and the output channels is input channels divide channels by parameter, which is by default set to 2 in the input. So it gives us where did it go? Yeah, so it's automatically set to 128 divided by 2, which is 64. So all the rest of the stuff is kept same, with batch norm and is training kept same. So this part is implemented, this one. I believe the non-linearity is also set to true, as you can see. So this part is covered. So what is going on, that the output from here is going to be scaled down, then it's going to go through a batch normalization layer, then it's going to be passed through an ELU non-linearity, and we are going to be here. So now we need to implement this 3x3 dilated CNN layer. So for that, what do we do is that if the channel multiplier is set to 0, that means we want a typical convolution layer, so we use this function. But if it's not set to 0, that means we want that channel multiplier thing, we want that separable convolutional layer thing, so we are going to use this operation. And in that case, in both cases actually, in this case the number of input channels and output channels is going to be same, and in this case also the number of input and output channels is going to be same, with the channel multiplier set to what we want it to be. Another thing important to know is that the batch normalization and ELU is also covered here, because the batch norm and is training is set to true. And I don't know what's wrong with my cell phone, anyhow. So that's that. And after that we have a final project up or scale up layer, which actually scales up the output to 128 dimension. So for that we actually use again a 1x1 convolution layer, but this time the number of output channels is going to be 128, and the input channel is reduced one, it's 64. Okay. And then there is this make two-dimensional Resnet function. So I actually went through this one as well. So you need to know that this is going to make 2 or more layers in the architecture, not just one. And this is going to use this function in it to actually make a block of a certain layers. So I'm receiving a call, and I'll continue with the rest of explanation in the next recording. I hope it helped you guys in any possible way. That's just the raw understanding that I've had so far.